Hello everyone, this is Rajesh of CIC. Now I'm going to give a seminar on diffraction. Firstly, diffraction, the process by which a beam of light or other systems of waves is spread out as a result of passing through a narrow aperture or across an edge, typically accompanied by interference between the wave forms produced. Next, diffraction takes place with sound, with electromagnetic radiation such as light, X-rays, gamma rays, and with very small moving particles such as atoms, neutrons, electrons, which show wave-like properties. Now, coming to the formula, d sin theta is equal to n lambda by d is the distance between slits, theta is the diffraction angle, n is the order number for maximum, lambda is the wavelength. As you can see in the diagram, this is the diffraction of a cube. Okay, this is the diffraction of a cube when laser light is passed through it. Now coming to the diffraction experiment. Diffraction was first observed by Grimaldi. As you can see in the diagram, this is the diffraction experiment where X-ray is incident on an obstacle and it is diffracted. Okay, now here S is the light source, AB is the obstacle, XY is the screen, and here light is incident on edge of the obstacle. Now coming to the diffraction phenomenon. Diffraction phenomenon, the phenomenon of bending of light waves incident on the edge of opaque obstacle and spread geometrical shadow is called diffraction. Now coming to source, types of sources. Here there are three types. One is point source, linear source, and infinite distance source. As you can see in the diagram, a laser light is incident on the opaque obstacle, and as you can see geometrical shadows, this is the diffraction. Now coming to wavefront, Huygens proposed the concept of wavefront. The locus of all space particles is called wavefront. Wavefront is of three types based on the shape of wavefront. They are spherical wavefront, cylindrical wavefront, and plane or linear wavefront. Now again, wavefront is of two types based on location. Okay, that is shape and this is location. Location between two screens. They are primary wavefront and secondary wavefront. Now coming to the difference between interference and diffraction. Interference is observed in all the waves. Diffraction is also observed in all the waves. This is proposed by Thomas Young and this is proposed by Grimaldi. Interference, modification of amplitude, density with superposition of waves. The phenomenon of bending of wave and spreading with geometrical shadows is called diffraction. Now coming to interference, interference is observed in daily life in oil drops or super bubbles. Okay, now coming to diffraction. Diffraction is also observed in daily life, as you can see in the sky, sunlight diffracts, right? Now coming to interference, intensity, amplitude are equally distributed. Now coming to diffraction, diffraction is observed in daily life in CDs, DVDs, shadow microscopes and telescopes, photography. Interference patterns. In interference patterns are bright image and dark image. Now coming to diffraction, amplitude or intensity are unequally distributed and diffraction patterns are maxima and minima. As you can see, these are the diagrams of interference patterns and diffraction patterns. See the interference patterns, okay, bright band and dark band, and in diffraction we have maxima and minima. These are the diagrams of interference and diffraction. Now coming to resolving power of grafting. Resolving power. What is meant by resolving power? The resolving power of a grafting is a measure of its ability to spatially separate two wavelengths. The chromatic resolving power R is defined by R is equal to lambda by delta lambda, which is equal to small n into capital N, where delta lambda is the resolvable wavelength difference, n is the diffraction order, and capital N is the number of groups illuminated. As you can see in the diagram, this is the resolving power of grafting diagram. Here we calculate the resolving power of microscope or telescope. As you can see in the diagram, this is the resolving power of grafting, right? Now coming to the apparatus, S be the infinite distance source, A be the width of grafting, theta is the angle of diffraction, d theta is the change in the angle of diffraction, theta plus d theta is combined diffraction angle, right? Now coming to XY, this is the screen of images. Here P is the position of original image, P1 is the position of first diffracted image, P2 is the position of second diffracted image, lambda is the first diffracted color, d lambda is the second diffracted color, right? Now when they both combine, they give the combined wavelength, right? So lambda plus d lambda is combined wavelength. Resolving power of grafting depends on, that's a question, right? So it depends on order of grafting, that is n, and total number of spatial lines, that is capital N. So rp is directly proportional to small n and rp is directly proportional to capital N. So rp is equal to n into n, where small n is the order of grafting and capital N is the total number of spatial lines. Okay, now coming to the resolving power of telescope and resolving power of microscope. Firstly, resolving power of telescope. Resolving power of telescope, let d be the diameter of the lenses in telescope and theta be the angle. Let d theta be the angular separation between the two objects. Then the resolution power of telescope is represented by 1 by d theta is equal to d by 1.22 into capital D. Now coming to the resolving power of microscope, let d be the distance between the objects, theta be the angle, and with the refractive index of medium. Resolving power of microscope is represented by 1 by delta d is equal to 2n sine theta divided by theta. These are the formulas for resolving power of telescope and resolving power of microscope. Thank you guys for giving this wonderful opportunity. This is Rajesh Kumar signing off. Thank you.